Hello and welcome to this new lecture of Latent Variable Models in the course AI 4009 Generative AI. Specifically, we will be looking at some of these latent variable models, how we construct autoencoders, and then we will, in a series of these videos, we will see how we can develop variational autoencoders for image generation. So we have been discussing about probabilistic models, given some data points. What we are interested now is to understand the distribution of this data. So for example, if there are 4 data points in this distribution, and right now I'm interested in what is the probability P of X for this distribution. So essentially that may be represented by the mean and the at least one variance of the data. So similarly for the conditional probability distribution, if we are given some X, so we are now interested in what is the probability of Y given this X. And as we have been discussing, that this X is basically representing the input data for us. So the probabilistic models are trying to estimate the probability of the variable. So you can see that we can estimate the probability of P of X given the individual probabilities, and we take the product of it. So for example, if we are solving this natural language processing problem where we want to take one word at a time and we want to predict the next word, for example, what is the probability of the next word think? So what we actually do is, this is the probability of x of 1 given x of 0. So since x of 0 is not given, so we can rewrite it as P of x of 1 because it is not depending on any of the previous ones. So the first word is I. What is the probability that the next word is going to be think? So this is what we are trying to do. So when we are predicting P of 2, probability of x of 2, we are taking all the input from 0 to 1. So essentially you can see, so the next input is I because this it was the previous input. And what was the output that was produced when we processed the previous input? So to predict the probability for the next word, essentially what we need the all the information from x of 0 till 2. So you can think like we are taking the think as the next input word and the history that we have produced from the previous. So this history is a sort of the information or the past information that has been produced or that has been in the context. So from the beginning, so you can see the information is being forwarded throughout till we input the last word here and then produce this last output. So essentially you can think that when we are generating this x of 6, it is ultimately affected by the word M as well as the previous words, all of these words that we have processed. So that's is going to help us in generating the context here. We also saw this one in the pixel RNNs, that if we want to generate the pixels, that is going to generate pixels in rows one by one. So you can see that we are generating the first pixel in the first row, and since we don't have any of the previous information, so we are not doing any conditional probability here. So we are just predicting the probability of P of x of 1. And then when we are predicting the pixel x of 2, we are taking the previous pixel as input and then also the output from the previous pixel. So you can see essentially the green means we are taking the input green as well as the output produced when we were generating this x of 1. So these two will help us produce the next pixel. So in the generation of this red pixel, you can see we are using this previously generated pixel and the history that is coming from all of it. So you can see that when we are predicting x of 3, we are using all of the information from x of 1 to x of 2. So all the previous pixels will be involved. So you can think like if I am going to generate this pixel and this is my complete image, then it means that all the previous pixels will be used to calculate its probability. So in the context of generative AI and for our lecture, we will be discussing these different types of variables, the observed versus the latent variables. So you can think like the observed, तो वो हैं जो कि डेटा हमें गिवन है, like x है, like उसका लेबल गिवन है, तो ये सारे जो है ना हमारे लिए ऑब्जर्व डेटा है. जबकि लेटेंट वो वेरिएबल्स हैं जो कि गिवन तो नहीं है लेकिन वो एग्जिस्ट कर रहे हैं डेटा के अंदर, हिडन फॉर्म के अंदर मौजूद हैं. सो दैट प्लेज एन इम्पॉर्टेंट रोल when we are generating the data or understanding the distribution. So इसका मतलब ये है कि हमें वो डेटा एक्सट्रैक्ट करना पड़ेगा, latent information या hidden information जो है डेटा के अंदर, which will be highly useful when we are understanding the distribution of a particular data. और दूसरे टाइप्स के वेरिएबल डिटर्मिनिस्टिक और नॉन डिटर्मिनिस्टिक या रैंडम जिसे हम we call them. तो डिटर्मिनिस्टिक तो वही हैं कि जो कि give us through a function directly we can calculate their value. जबकि random which we also call them some sort of a stochastic variables हैं, तो these are basically giving us the probability distribution. तो जब ये हमें probability की बात हो रही है तो हम कोई exact value इससे derive तो नहीं कर सकते, but we can generate random numbers or random values out of that. So latent variable models की अगर हम बात करें तो essentially this is going to be the probability distribution for the random variables. तो x तो given होगा हमारे पास, we need to derive this latent representation z, and of course for the model we need to understand their weights. So here x is the way observed or the given variable, and z is what we call it the hidden or the latent variable, and then we want to understand this probability distribution over these two variables, how the data looks like. So this is a simple graphical example of the distribution of the data. अगर यहाँ पे देखें we can see visually, अगर आप देखें 3 colors भी generate हुए हुए हैं, तो seems like there are 3 groups of data. तो जब we talk about 3 groups of data, इसका मतलब ये है कि this one has its own mean and a variance, this should have its own mean and a variance, and then this one has its own mean and a variance. So let's say these are represented by these visual distributions, Gaussian distributions. So and everyone has its own weight vectors associated with it, इसके अपने mean और variances हैं, so on and so forth. So what actually we mean here is this data is so complex that it cannot be represented by just one Gaussian, a simple Gaussian. So in fact we have multiple Gaussians, so that's why we call it the mixture of Gaussians. The data distribution is much more complex, so we need more than one distribution or more than one Gaussian in order to understand it. And to derive this one, we simply do something like probability of x. We can break this one into a conditional and a marginal distribution. So here p of x given z, so we are trying to understand what z x looks like given some hidden representation z. Now the question is, how can we calculate this hidden representation? We will see how we can do that and the probability of those hidden variables. So we can do the same thing for the conditional probability, where I'm interested in predicting the label, for example, for a particular data. So we can say probability of y given x can be computed by summing over all these z's we have, and we are taking the conditional probability of y given x and z, and then the probability of this z. So now here you can see essentially the addition of this x and z together. Instead of here we are just using this z, and now this is conditioned because we are interested in the label of an object. Let's say I'm interested in finding the type of object, like is it a dog or is it a cat or is it a human. So that is what the labeling I'm doing. So the latent variable models can do both regression, classification, as well as now we will see how we can do the generation process. So this is the basic idea which we actually need to understand, is what we are trying to do. If we are right now, इसमें एक चीज़ अगर आप नोटिस करें, this is where this will come from, that is the question. अच्छा, PFZ हम देखेंगे, we can select a very simple distribution by ourselves. हमने कहा कि जनाब okay, let's consider a Gaussian distribution with zero mean and unit variance, that is 1. So it's just like we have we can generate random numbers between 0 and 1, or between this range of the values between -1 and a +1, since we have the unit variance, and then it's zero mean. So where the story starts actually, अगर आप इस चीज़ को गौर से देखें कि this is the P of Z that we consider it. So we have some mean somewhere and some variance of the data. तो ये तो हमने select कर दिया अपनी तरफ से, और P of Z जब हमने randomly select कर लिया है, which is a Gaussian, and we intentionally make it easier, I am interested right now in generating the probability distribution P of X or Z. I should say that I am now interested in estimating the distribution P of X given Z. So now given Z is right here. So उस इंटीग्रेशन के अंदर अगर आप देखें P of Z तो मैंने सेलेक्ट किया है, so it's a known, and now this is what I am trying to know, what is it. So उस चीज़ को estimate करने के लिए what we are trying to do is we are employing a neural network. So essentially इस neural network को मैं अपनी distribution दूंगा, तो so this is just going to give me an estimate or some probability distribution for P of X, and this P of X can be calculated when I take the product of this P of X given Z and P of Z. तो ये जो network basically मुझे दे रहा है P of X of Z. And when I'm interested in this P of X given Z, essentially I am looking for the mean and the variances for this Z vector. इसका मतलब ये है कि इस नेटवर्क का जो आउटपुट है, I'm not expecting a label, I'm not expecting some specific value. In fact ये मुझे vectors देगा for mean and the variance for this normal distribution. तो वो मीन एंड वेरिएंसेस ये प्रेडिक्ट करके देगा, तो उन मीन और वेरिएंसेस में से मैं डेटा को ड्राइव करके मैं एक प्रोबेबिलिटी डिस्ट्रीब्यूशन बना सकता हूँ. और इन सिंपल वर्ड्स, अगर मुझे एक रैंडम नंबर्स दिए जाए एंड ऑफ कोर्स वी हैव सम लेंथ ऑफ दिस जी, उसको नेटवर्क में से पास करा के कोई मीन्स और वेरिएंसेस में लेकर आऊँगा, उन मीन्स और वेरिएंसेस में से डेटा को सिलेक्ट करके एक इमेज जनरेट करा सकता हूँ. दिस इज़ व्हाट वी कैन थिंक लाइक. तो जब हम जनरेशन की बात करेंगे तो यू कैन थिंक लाइक दिस, एनी ऑफ द डिस्ट्रीब्यूशन, when we know that this is the mean and this is the variance, then we can select any of the data points inside of it. So think like this, अगर सारे पिक्सेल्स के लिए एक मीन और एन वेरिएंस गिवन है, जस्ट एन अजम्पशन, तो हर पिक्सल के लिए मैं फॉर एग्जांपल पिक्सल 1 के लिए यहाँ से मैं एक वैल्यू उठाऊँ, इसी तरह पिक्सल 2 का अपना डिस्ट्रीब्यूशन है, तो फॉर एग्जांपल मैं वहाँ से कोई मीन एंड वेरिएंस को देखते हुए एक वैल्यू में उठा. सो एसेंशियली आई एम ट्राइंग टू जनरेट an image n by n, उसको grid में रख के I can generate an image. But the question is, how can I get this distribution for every pixel, is where this model will help me out to get that distribution. So essentially what we are trying to do is we need to give the training examples to the network, and then this is going to understand from that distribution of the training samples. तो इसका मतलब ये है कि जो ट्रेनिंग सैम्पल्स हम देंगे, उस ट्रेनिंग सैम्पल्स जैसे ही आउटपुट ये हमें देगा सीख के. तो बेसिक स्टेज ये है कि गिवन दीज सेट ऑफ रैंडम नंबर्स, क्या उसको न्यूरल नेटवर्क के थ्रू पास करके क्या मैं पी एफ एक्स ऑफ जी गिवन जी को क्या मैं एस्टिमेट कर सकता हूँ. सो आई एम यूजिंग दिस वर्ड एस्टिमेट, क्योंकि वो रियल कैलकुलेशन नहीं है जिसमें बाय हैंड हम इंटीग्रेट करके सारी वैल्यूज़ हम जनरेट करें. इन फैक्ट इट्स एन एस्टिमेशन ऑफ दिस पी एफ एक्स गिवन जी. सो इसको सिंपल अंदाज में अगर हम देखें तो अगर हमारे पास कोई रैंडम नंबर जी हैं तो व्हाट इज़ द प्रोबेबिलिटी टू जनरेट दिस इमेज एक्स, राइट. सो दिस इज़ व्हाट वी आर ट्राइंग टू डू. तो ये वाला काम जो पी एफ एक्स है उसके लिए ये दो चीज़ें चाहिए, पी एफ एक्स गिवन जेड. तो पी एफ एक्स गिवन जेड के लिए मैं काम करूँगा जनाब एक न्यूरल नेटवर्क बना दूँगा, और पी एफ जेड तो ये एक रैंडम वेक्टर है जो कि कोई गॉसियन डिस्ट्रीब्यूशन से मैं उसका लेंथ डिसाइड करके लेट्स से 20 चाहिए 30 चाहिए एलिमेंट्स, वी can draw that. So this is just a visual explanation of what we are trying to do. What Z actually represents is Z, using this Z we can map or generate any of the available this X. So think like this, अगर मेरे पास X means every point is an image, तो यहाँ Z में से कोई भी डेटा मैं उठाऊंगा तो वो मुझे एक इमेज जनरेट करके देगा, but that image may not be a random image. In fact that is from this distribution, यानी जो ट्रेनिंग किया है हमने डॉग्स के इमेजेस हैं तो ये डॉग्स जनरेट करेगा. That's why we have this mapping. This is not going to randomly map somewhere else. So this is what we are trying to do. This Z has been generated in such a way that using this Z it can map to some of these, any of these axes. So essentially in simple words we can think like the latent representation is done in such a way that it should regenerate the images. Those are very much similar to the data on which it was trained. So यही काम अगर आप देखें डीप लर्निंग के अंदर इन लेटेंट वेरिएबल्स को इसी तरह काम करेंगे कि so we are given Z which means a set of random numbers. We will see कि अब आगे auto encoders में how we can basically encode this Z from given input training data. So assume करें कि यहाँ पे P of Z है हमारे पास. So the distribution of these random numbers are being given. You can see like Z drawn from P of X, which means that we randomly generated some Z. उसको neural network के कुछ layers में से हमने pass कर दिया. So this is essentially going to give us an estimate of this probability of X given Z, and here theta is the weights of this model, and then we are going to generate an image like this. So ये जो concept है ये basically use हो रहा है variational autoencoders और gains के अंदर भी, और इसी तरह normalizing flows के अंदर we will see how we can work with it. So this is what essentially an example, the upper portion is basically representing. You can think like this. Essentially अगर आप एक चीज़ देखें, this is a smaller vector and in one dimensional, and we need this model should be able to generate a two-dimensional image. इस केस के अंदर अगर आप देखें, because we are interested in generating an image here. So ये जो up convolution है तो essentially we have a smaller input and then we are trying to generate larger output to match whatever the information that we want to do. So essentially आपने सुना होगा convolutions का. तो convolutions are essentially when we apply without pairing, what they do is they reduce the spatial dimension and extract the features. So एक और convolution करेंगे तो ये और भी छोटा हो जाएगा depending on the size of the kernel plus the stride that we select. But यहाँ पे अगर आप देखें इस portion में, इस half के बाद अगर आप देखें, we are given a smaller image, think like this, and we are trying to upsample it or increase its spatial dimensions. So this is what we use this transpose convolutions here. An example of these transpose convolutions you can see here. These are also known as fractionally strided or deconvolutions. So let's say we are given this image and we have this kernel. So as usual we use the standard kernel. The only thing that we do is first resize this one in such a way that we are inserting some rows, alternative rows here. You can see after every element, every row in the original, we insert one row. So essentially every element that we have, it's all zeros here. Similarly, we do the insertion of columns, every alternate column in the original image. So we are inserting. So you can see the spatial dimension has increased. But then we apply this kernel. Remember that if I apply this kernel without pairing, essentially I'm reducing this size up to here. So this is what we don't want. So in order to preserve, now this is the input for applying actually the convolution, this whole image. So to preserve its spatial dimensions, essentially we need to do zero pairing, and then we start convolution. So that is what one of the examples of how we can do this upsampling or sort of dilating or dilation convolutions can also be applied here. So this is the example as we have seen. तो जो latent variable models हैं हमेशा याद रखें deep learning models कोई भी हो उसको के लिए training data चाहिए, and apart from the other setup एक और चीज़ जो कि important है its loss, how it is performing on the training data. So we should know the performance of the model. तो जो latent variable models है उसके लिए usually हम use करेंगे negative log likelihood here. So log of probability of x of I z. So whatever the probabilities we are estimating, we are trying to minimize this term कि चूँकि negative है यहाँ पे तो उसको minimize this expected log likelihood, और उसका actual function हम आगे जाके देखेंगे कि what we actually do when we are working with the variational autoencoders. So we have been observing that deep learning में वहीं हमें gradients calculate करने पड़ेंगे, and based on those gradients we need to go back and update the weights. So same is the case here. We are applying gains के अंदर थोड़ा सा इस चीज़ को भी हम देखेंगे expected value of p of z given p theta x of z x given z, and a normalizing flow may basically those are performing some sort of invertible mapping from z to x. We will see how those are a little different that we are working. So given some training data, let's say x1 x2 to xn, here these are basically think like the individual images. These are not the features. So this is image 1 2 3 and we have n number of images, and we want to train a model to predict this probability of x for all these variables. So you can think like we are generating an image, and to do that we need this theta. So the model will learn which is the best theta for us, and we are trying to maximize this probability. ये जो भी हमने probability value calculate किया है for every image sample we have x of I images, उनका probability जो है p of x, we don't want to be a smaller value, we want to have a higher value for my inputs. So that will be my objective. तो जितने भी probability में predict करूँगा उस distribution का, that should be the maximum that I want. तो उसको तो we have n number of examples, तो हर एक के लिए log of p of x calculate करके उसको sum करेंगे, and we usually average it out by dividing it with the total number of examples images in my training data set. And we need to select these theta in such a way that this p of theta of x of I is the maximum for the whole training data set. तो ये तो आपको मालूम है कि we have just written this formula, so we need to integrate over p of x given z times the probability of this z, and we can just put it here, and then we can find this term here by using this neural network. But there is one problem. वो problem ये है कि this is the distribution that we have selected and it's easy, there is no any issues about this one, but this is a little complex here in a sense कि it's intractable, in a sense that we need a lot of resources, a lot of time to calculate it, and it becomes really infeasible for us to calculate because we are integrating over all the possible values. Just for an example, understand कि जनाब x जो है ना उसका जो dimension है, let's say how many dimensions that we want to keep for this z is important. Let's say if we have 20 and assume करेंगे जनाब हर pixel का जो possible value है वो binary है 0 और 1. So essentially we need to integrate over 2 to the power 20 different values. So this is going to be a huge number. So integrating over all those possible values in terms of अगर आप calculation के point of view से देखें, this may not be tractable for us. So there is a need to change this one कि manually उसको integrate करने throughout for all the possible values. So that is not a feasible solution. So instead what we do कि बजाय इसके कि हम उसकी ओरिजिनल वैल्यू को इंटीग्रेट करें बाय हैंड, वी कैन यूज़ एन एक्सपेक्टेड वैल्यू इंस्टेड। तो एक्सपेक्टेड वैल्यू मीन्स उसको हम एस्टिमेट करें कि जनाब वट एवर वी हैव एस्टिमेटेड इज़ जस्ट लाइक इट इज़ रिप्रेजेंटिंग द ओरिजिनल इंटीग्रेशन हियर। तो उस चीज़ से हम बच सकते हैं। सो इंस्टेड ऑफ दैट what we call it the integral, we just remove that integral and we are just using the expected value of this p of z given x. अच्छा, इसमें there is one problem here. So we just change this one into some sort of a representation. You can see here the expected value of p of z given x into the log of p of theta x of I, and now this is the joint probability that we have. तो अब again the question is how to calculate this one, though which is the posterior. हम इसको हम कैसे calculate करेंगे? हमारी assumption ये है कि जो z हैं and जो हमने calculate किया है using these x's, so this is like probability of z is given x of I. तो this is correct. We are assuming कि ये ठीक है. And then we need to calculate this actually p of z is given x of I. तो इसका मतलब ये है कि x of I तो given हमारे पास images हो गए for example, उनमें से हमने latent variables predict करने हैं जनाब. Now that is the question that we need to do. So think like this कि x's जो है ना given है, training images given है, उनको हमने transform करना है z के अंदर. z में से फिर जनाब हमने दोबारा से कोशिश करना है कि वही एक्सेस को रिप्रोड्यूस करें, एंड दैट इज़ व्हाट द ऑटो इंकोडर इज़ गोइंग टू डू, कि अब इसी के प्रोबेबिलिटीज़ हम कैलकुलेट करने जा रहे हैं, एंड दैट्स व्हाई वी आर कॉलिंग इट द probabilistic inference here. So this is the posterior that we are going to generate. तो इसका मतलब ये है कि हमें जो है ना p of x given है, which means the images का जो distribution है we know it, and to learn this p of z given this p of x of I, somehow we need to go through another neural network that is going to give us this probability of z given x of I. तो ये हम देखते हैं कि जनाब how we can do those things, and we are assuming कि जनाब ये जो p of z given x of I है उसको हम कैलकुलेट करने जा रहे हैं. To calculate this log p of x we need this term, और इसको अगर हम एक काम करें कि assume कि जनाब हमारे पास एक probability distribution है q of I of z है, and that is basically nothing just a normal distribution with mean and variances. Okay, so this is another that we have selected. We just assume that this is, and this is basically we want to be similar to this one. This is just replacing this p of z of x of I. I mean, this is just a simple representation of p of z x of I. So what we want to do, ये जो q of I of z है जो हमने assume किया, this should be very much similar to this p of z of x of I. चूँकि estimation है, we can just assume that this is a normal distribution, and we are trying to make it very much similar to what the p of z actually given x of I है. So we are just doing one thing here for mathematical stuff to include this part into it. अगर इसी distribution से divide और multiply करें तो we don't have any issues because this is going to be 1 actually. लेकिन this is going to help us out in doing one thing कि इसको अगर हम rewrite करें, so we have p of x of I given z and we have p of z divided by one part is here. लेकिन if we look at this integration over this q of I of z is basically summing out, because we are just considering it an expected value. So this is basically the integral is gone and we just want this one to be an expected value. So the z sampled from q of I of z, and q of I of z is, we assume that this is a normal distribution, तो उसके लिए means और variances हैं हमारे पास. So मेन थिंग यहाँ पे अगर आप देखें कि जो इंटीग्रल है उसको हमने ख़त्म करना था और उसकी जगह वी हैव इंट्रोड्यूस दिस एक्सपेक्टेड वैल्यू ऑफ q ऑफ I ऑफ z, and now this equation can be implemented or we can solve by making little change. तो ये तो हमारे पास मौजूद होगा क्योंकि this is our assumption and we are just generating it, and the only thing that we need to condition is to be similar to the actual जो probability of z given x of I होना चाहिए, and then these terms p of x of I given z जो कि न्यूरल नेटवर्क कैलकुलेट करके देगा, ये हमारे पास मौजूद है, ये भी हमारे पास मौजूद है. So this log of p of x of I can be now calculated. तो यहाँ पे ये जो काम हुआ है इंटीग्रल को एक्सपेक्टेशन में जो कन्वर्ट हुआ है, इन इक्वेशंस को आपको समझने की ज़रूरत है, which is basically the basic idea of the probability of integration and the expected values. So एक और assumption जो कि बहुत important है in terms of these variational approximations, and that is Jensen's inequality. इसको ज़रा गौर से देखें कि अगर हमारे पास कोई वेरिएबल है y, and the log of expected value of y is always going to be greater than or equal to, अगर log को हम अंदर लेके जाएं log of y and then फिर expected value calculate करें, so this is always going to be the greater than this one. So this you can think like this is the lower bound of this. So what this means is whatever we make the changes to this one, the log of y and then its expected value will always be, this one will be always smaller or maybe equal to, but it cannot be greater than, and this is assume कि ये जो है ना ऊपर वाला distribution है हमारे पास. So keeping that thing in our mind, one of the important ये वाला जो अभी equation हमने derive किया है, what we are trying to do is इस log को अगर मैं यहाँ पे push कर दूँ and just keep all of the terms the same, सिर्फ इसी theorem को apply करने के लिए उसकी requirement है आगे हमारे लिए. So what does this means कि ये जो p of x of I होगा, log of p of x of I, we ensure using Jensen's inequality कि this will be going to be always greater than or equal to the right hand side, this one. So this has an important concept. Just before going to that, log के property अगर हम इसके ऊपर apply करें, you know log of n divided by m, it's going to be log of m minus log of n. So same is the case here. तो ऊपर वाले portions यहाँ पे देखें, log of p of x given z plus log of p of z, and बाहर चूँकि ये expected value of this q of I of z भी है, तो so we have expected value of q of y of z. नीचे वाला term जो है ना ऊपर जाके minus होगा, so minus outside term times the log of q of I of z we have. So this is the equation that we have, and as we mentioned that we want this one to we try to maximize this one. इससे मुराद ये है कि जो z से हम जो images निकालेंगे those should be very much similar to whatever the input we have here. अच्छा जनाब, so the next thing अगर आप एक चीज़ notice करें, this is what we call it the entropy. Entropy is just, this is the equation of the entropy, probability of some variable x of I times its own log of probability, and if we sum it over all the samples I is equal to 1 to n, then this is what we refer to it as the x of I. तो यहाँ पे variable अगर आप देखें q of z है और यहाँ पे भी q of z है, and this log, so we can represent this one as a simple the entropy of this variable q of I. So बाकी rest of the things are exactly the same. लेकिन इस चीज़ का अगर आप एक चीज़ notice करें, this term and the addition of this entropy term plays a crucial role here. And what is that? Before that we try to understand this entropy. What this entropy means, as we said, the p of x into log of p of x, and we integrate it over all the possible values of this variable x. So in case of our what we say the continuous values, so we are just continuing that. लेकिन अगर हमारे पास discrete है तो of course that will be a summation here. So इस चीज़ को understand करने की कोशिश करें. What this entropy means here, Generally, the definition of this entropy means is the randomness in a data. So what this randomness has to do in our equation, because this has some contribution in our data in this equation. If you look at this one, generally the entropy, if the probability of certain event, let's say x is equal to 0, and if we know that it's always going to be 0, यहाँ पे देखें इस साइड पे entropy है, and then we have on the x-axis we are going to have this variable x. So if we know that x is always going to be 0, so there is nothing new in it, or there is no any randomness in it. Or if I know that the always this one is going to be 1, so there is no any entropy is 0, there is no any randomness. Lekin if you look at this one, if I know that p of x is equal to 1, इसका probability 50% है, so then इसका मतलब ये है कि there is highly unprobable. तो इसका मतलब ये है कि we are going to have the maximum entropy, because the 50% of something I'm not sure what will be the next other 50%. So that is where we have the maximum entropy, you can see. So the highly random जहाँ पे भी probability होगा, that is going to give us the high entropy over there. So in terms of our process, what this h of q of I is doing, or the entropy of this variable q is doing, distribution q is doing, is ये वाला portion अगर आप देखें तो our model is trying to maximize this term. What does this means is, given some z vector, it is trying to generate these x of I, and if we want these x of i's to be very much close to whatever the original images are, or the training example. Dog है तो dog generate करना चाहिए, cat है तो cat generate करे. So this is the, so in other terms we want its probability to be maximum होना चाहिए, right? So that is what this term is essentially doing, is this one. तो ये अगर मेरे पास original data का distribution है, तो in equation this portion, or effectively this portion is this smaller one अगर आप देखें. So this is trying to do the maximum यहाँ पे, लेकिन उससे बाहर नहीं जा सकता. यहाँ पे हमने जैसे ही हमने डिस्कस किया था जेनसन्स इनइक्वालिटी में, दी पी ऑफ एक्स से बाहर कोई भी नहीं जा सकता यहाँ पे. सो दिस इज़ ट्राइंग टू डू दिस. लेकिन अगर आप देखें ये बहुत ही कमज़ोर सा है इन टर्म्स ऑफ, इट्स अ वेरी थिन वन, राइट. इसको कुछ खाने पिलाने की ज़रूरत है. सो टू द एडिशन ऑफ दिस टर्म इज़ डूइंग लाइक दैट, इसको कुछ खिला पिला रहा है. So the addition of this randomness is trying to make this distribution a bit thicker here. What does this means? पहले तो यहाँ से samples में drive कर सकता था, अभी चूँकि randomness हमने introduce किया है कि so then I can drive much more of the samples out of. And interestingly, these samples are similar to this original P of x. This is what I want, कि diversity मेरे उसके अंदर होना चाहिए. So if someone asks you, if you look at these two distributions, P of x and this P of x, this one has low entropy, because what this means, there are small number of possible values that I can select. So randomness कम है यहाँ पे. But if you look at this one, it has high entropy, so we have a much more possibilities of selecting the data over here. So this is what the impact of addition of this entropy term inside this equation is going to help us out. So this is what we want. We want a diverse set of values coming. Those are similar to whatever the original distribution that we have. So entropy plays that role. Number second. अच्छा, वहाँ पे एक और क्वेश्चन हमने बात की थी कि whatever the q of I we have selected, we want this one to be very much similar to this p of z given x of I. तो इसका मतलब ये है कि x of i's में से z's हमने जो बनाने हैं, अब कोई तो हमें बताएं कि जनाब ये actually is an estimate of q of I of z is basically an estimate of this one, then it means that these two should be very much similar to each other. So that's where comes the KL-Divergence. KL-Divergence basically दो distributions में distance हमें देगा. So this is what the formula is. KL divergence between Q and a P is represented like this. D of K of L is going to be the expected value of x drawn from Q of x into the log and the ratio of Q of x divided by P of x. So essentially this is the formula. इसको अगर हम log वाला सीधा करके लिखें तो ये negative term तो as it is मौजूद है. ये अगर आप notice करें, this is again nothing, it's just an entropy of this variable distribution Q of x or log of Q of x. So instead we have written like h of Q. Again it is the entropy here. So इसका मतलब ये है कि this KL divergence is also telling us the same thing that we have been discussing. लेकिन ये हमारे लिए यूज़फुल होगा कि what we are actually trying to do in the next is in terms of our KL divergence, we also need this term. So how can we feed this term inside our equation? इसको ये देखें, this is the original equation in terms of हमारा जो अभी equation derive किया है. So one thing that I just want, ये equation हमने अभी देखा है and we have said कि जनाब this p of x of I will be greater than or equal to the expected value of z given q of I of z plus into this log of p of x of I given z plus log of p of z plus the entropy. यहाँ पे अगर आप this is what we call it, we usually represent it L of p of q यहाँ पे जो, and we use it as a loss function or an objective function, and what we call it the evidence lower bound. और एक और चीज़ याद रखें कि this is always going to be smaller than or equal to p of x of I. This is what we are trying to do here. So the question is, what is a good q of I? That is the question. हमने कहा था कि q of I of z will be actually an estimate of p of z given x of I. तो इसका मतलब ये है कि the q of I of z को good इसलिए कहेंगे कि which one that is very much similar to this one or gives us a very good approximation of p of z given x of I. So that's where we also need to include this KL divergence term here. अच्छा, तो इस चीज़ को इंश्योर करने के लिए KL divergence हमें चाहिए, and what we want KL divergence between Q of I and P of Z given x, कि ये दोनों बिल्कुल एक दूसरे के सिमिलर होने चाहिए because Q of I is of Z is going to estimate this P of Z given x of I. So let's put this one in the equation, or if we rewrite it in the form of terms को log की property इसके ऊपर apply कर दिया, and when we rearrange these terms तो ये तो as it is मौजूद है. इस चीज़ को ज़रा गौर से देखें. This is just E of Z Q of I of Z log of Q of I of Z. This is just the entropy of Q of I. So again this is the entropy term. और दूसरा यहाँ पे अगर आप एक चीज़ नोटिस करें कि this is P of x and this is Q of I of x, expected value of Q of I of z. So this one has nothing to do with this. So this is a constant term compared to this one, the expected value. So this will vanish out. तो वो जो log का जो property होता है, अगर एक हमारे सॉरी ये इंटीग्रल का जो property है वो यही है कि अगर ये इसके ऊपर डिपेंडेंसी नहीं है तो that the probability of that term is going to sum out integral out to 1, or the only thing that remain will be log of p of x of I for us. So this is the final term. अगर आप इस चीज़ को notice करें कि we have already seen this is the exactly the same term that we have, which we call it L of I of p of q of I, which is the evidence, we term it as the evidence lower bound, in fact this one also, but these are all coming negative, so we have put it as the negative of the evidence lower bound plus this log of this p of x of I. और यहाँ से हमें तो estimate करना है log of this p of x of I, so we can take it इस चीज़ को अगर हम उस साइड पे भेजें, so the final term that we are going to have is this one, कि log of p of x of I को estimate हम करेंगे, and this can be implemented. Now we will see it is equal to the KL divergence between these two distributions and plus the evidence lower bound. तो इसमें सिर्फ आप गौर से देखें, ये चीज़ हमारे पास गिवन नहीं है, जी चूँकि नहीं है, और यहाँ पर अगर आप देखें ये चीज़ हमारे पास गिवन नहीं है. सो एंड दिस इज़ व्हाट वी आर अज्यूमिंग बाय आवरसेल्व्स. हम एक रैंडम वेक्टर्स हम जनरेट कराएंगे. सो नाउ द क्वेश्चन इज़ हाउ कैन वी एस्टिमेट दैट. इन दोनों चीज़ों के प्रोबेबिलिटीज़ को देखने के लिए we will be essentially using two neural networks to estimate these two values. और दूसरी बात अगर आप ये देखें, this is always going to be ज़ीरो या पॉजिटिव है, right? एंड इसका मतलब इसकी जो डायरेक्ट डिपेंडेंसी है दैट इज़ द एविडेंस लोअर बाउंड. इसको जितना हम बढ़ाएंगे दिस इज़ ऑलवेज गोइंग टू बी लेस देन और इक्वल टू दिस log of p of x of I. So we are trying to do the KL-Divergence, or you can say the distributions to be very much similar. Exactly similar हैं तो KL-Divergence ज़ीरो है, लेकिन जितना ज़्यादा होगा इसका मतलब that is what we need to reduce this one. So that will be the final equation for these variational approximation, which we can actually work out and then we can see. So what we are trying to do, we are trying to maximize this one. So this is what objective. We want this one to be as much maximum as possible, and we want to minimize this divergence. In other words, जो हमने जो distribution consider किया है, there should be very much similar to the p of x given z's, z's given x, yeah, p of z's given x. So that distance should be minimum. I mean, the minimum distance से मुराद ये है कि बहुत ज़्यादा सिमिलर होने चाहिए, और इस टर्म को हम मैक्सिमम करने की कोशिश करेंगे उस मॉडल के लिए. So this is what exactly going to happen. So we are given some training examples. We select the training examples और उनका हम gradient हम calculate करेंगे to update those weights. So objective function तो ये हो गया evidence lower bound, और then we select one sample, और उस sample के against में हम एक approximation कर रहे हैं इस p of x of I given z, ये using this evidence lower bound, और फिर हम अपना जो variables हैं वो हम update करेंगे. So this is going to be the what we call it the derivative part, जो कि gradient आ गया, और इसको learning rate के साथ हम multiply करके उसके weights को हम update करेंगे. This is an example we have seen several times in this deep learning course, and we try to update these Q's so that this L of I of P Q of I जो है ना वो maximum होगा. तो यहाँ पे सिर्फ एक प्रॉब्लम ये है कि इसको विजुअली अगर आप देखें, so we are given some z's, we have a neural network that is going to predict this x is given z's. तो in other words अगर latent representation दें तो उससे हम x's हम बनाने जाएंगे images, and we want this p to be maximum. By p to be maximum से मुराद ये है कि सही images जो कि ट्रेनिंग डेटा जैसे में हैं उस जैसे बनाने चाहिए. एक और न्यूरल नेटवर्क है जो कि x इनपुट लेगा और उसके अगेंस्ट में z's को जो है ना वो प्रेडिक्ट करेगा. सो लेटेंट रिप्रेजेंटेशन, सो दिस x में से z लेके वो हिडन रिप्रेजेंटेशन लेके आएगा. यू कैन थिंक लाइक कि हमें वो जो क्रक्स है या जो इम्पोर्टेंट फीचर्स हैं उनको ये रिटेन करें एंड द रेस्ट कैन बी डिस्कार्डेड. थिंक लाइक दिस. सो z शुड बी a very good representation of this x. तो इसको हम latent इसलिए कह रहे हैं कि because x is given but z is not given, which we are trying to produce. So from x is, अब बाद में जाकर अगर आप देखें this is a separate network and this is a separate network. तो autoencoders जो है ना इन दोनों को मिला के काम करेगा. So what happens कि x given हो तो वो हमें ये वाले z's दे दें और z's को यूज़ करते हुए दोबारा से हम x's प्रोड्यूस करें. And this is just going to be as we mentioned, it's a normal distribution with means or variances. यानी इससे मुराद ये है कि ये जो नेटवर्क हमें आउटपुट कर रहा है ये कोई स्पेसिफिक वैल्यूज़ या एक्सेस या पिक्सल्स नहीं करेगा. इनफैक्ट ये एक डिस्ट्रीब्यूशन हमें बता देगा, उसमें मीन्स और वेरिएंसेस. गॉसियन डिस्ट्रीब्यूशन है तो हम चाह रहे हैं कि गॉसियन डिस्ट्रीब्यूशन हमारे पास. इसमें एक प्रॉब्लम है, अगर हमारे पास हर पिक्सल के लिए मीन और वेरिएंसेस हों एंड इन नंबर ऑफ हमारे पास पिक्सल्स हों, then we are going to have a large value that we need for representation of this network, which is complex in a sense. एक और issue जो है वो derivative of a random numbers is not possible. तो उस चीज़ को सॉल्व हम कैसे करते हैं, वी विल सी इन अ नेक्स्ट वीडियो. And I would like to say thanks to Dr. Sergey Levine. He provided me the permission to use his slides, and you can check his slides from this link. Okay, see you next lecture.